So with this next section, implicit differentiation, I'm just going to say straight off the bat that what we're doing here, we're going to have to use Leibniz notation because this was developed and it's easiest using his notation because we really have to know our independent variables when we're going to be dealing with this. And what's happening here is we want to talk about what if we want to find a derivative of a relation that is not a function. For example, y squared equals x. Because y squared equals x is a parabola opening to the right and therefore violates the vertical line test. One thing we could do is that we could say, well, let's go ahead and isolate y like we normally do. But because I'm introducing the square root, I do need a plus or minus. And what I really have here is two separate functions. Y equals the negative square root of x, which is the bottom half of the parabola, and y equals the positive square root of x, which is the top half. And then I'd have to figure out, okay, for each of these, what's the derivative for each piece? And then which piece is it that I need to use? But what if I'm using both pieces? It gets complicated very quickly. So what we do in this case is we're going to do what's called implicit differentiation. And we do need to use Leibniz notation for derivatives to help us keep track of the independent variable. And our first step is to figure out what's the independent variable, and then start taking my derivatives. But anytime I come across a variable that's not the independent one, I have to treat it like it's a function. And I'm putting function in quotes because we realize we don't have functions, but it's a lot easier than saying a relation that's not a function that is dependent on the independent variable. But the idea of this is it's some unknown function that requires the chain rule. So if I go back to my first example here, what we would say, whoops, sorry about that. What we would say is, okay, let's leave it as y squared equals x. And I want to find dy dx. Remember that this is telling me find the derivative of y with respect to x. So this means that x is the independent variable. So if x is the independent variable, that means anything that's not x, oh, sorry about that again, anything not x is dependent. And I'm going to have to treat like it's an unknown function that needs the chain rule. So in this case, I'm going to start on the right side of the equation just because it's a little bit easier. X is an independent variable, so I just take the derivative of x using my shortcuts, and derivative of x to the first is 1. For the left-hand side, the y squared, I'm going to go ahead and say, let's find its derivative using our shortcuts. This would be the power rule. So I'd have, bring the 2 down in front, the base doesn't change, subtract 1 to get my new exponent, so 2 times y to the first. But then, because this isn't my independent variable, y is some unknown function. So I'm going to need to multiply by whatever the derivative of y with respect to x is. And I write the times dy dx because I'm saying I don't know what that is, but I know I need it because of the chain rule, since y is a dependent variable. It's a function of x. But that's what I'm looking for. And now I can isolate this by divide both sides by 2y. And I get dy dx is equal to 1 over 2y. And there's my derivative. This looks different for us in terms of an answer because we have not actually done a derivative where y shows up in the derivative. This typically happens when I'm dealing with things that are not functions because of the fact that they violate the vertical line test. If it is a function, usually it'll just have x's, but not always. Benefits to this. If you notice, I didn't have to isolate y. I could do the derivative and then isolate dy dx. So there are even times when I have something that's a function, but it's too big of a pain to isolate y. So I'll do implicit differentiation on that just because it makes for easier algebra. This is weird. It's going to take getting used to, and I know there are going to be questions in class over this. I did want to get through some examples here. So first example, we have x squared plus y squared equals 25, which is a circle centered at the origin with a radius of 5. And I want to find dy dx at the point square root of 20 square root of 5. Important thing to note, I'm looking at x as the independent variable, which means anything that's not x is a function of x and requires chain rule. So x squared, that's just x's in it, so I just do that like normal, 2x. And I have my plus. Derivative of y squared is 2y, but y is a function of x, so I need to multiply by whatever the derivative of y with respect to x is. Then I have my equal sign, and then derivative of 25 is the derivative of constant, which is always 0. I can then isolate my dy dx, and I have a formula that will find dy dx for any point I need. So to use the point given to me, so dy dx such that we're at the point square root of 20 square root of 5. I plug in square root of 20 for x and square root of 5 for y, and there's my slope at that point. Now, if I wanted to, I could simplify that and I get -2, but I'm not required to simplify it. Slightly more challenging examples. What if I have multiple variables? More than just x and y. So here I have x plus y plus z equals 10x. It makes kind of a saddle shape if you're trying to graph this. If I wanted to find dy dx, again, what I'm noting is that x is the independent variable, so that means anything not x needs the chain rule because it's a function of x. So that's true for y, but that's also true for z because z is not an x. So when I take the derivative of x with respect to x, that's just 1. Then my plus sign. The derivative of y is 1, but times dy dx plus sign. Derivative of z is 1, but that's not my independent variable, so I need the chain rule dz dx equals derivative of 10x will just be 10, and that is my independent variable, so I don't need the chain rule. Then I just need to isolate dy dx because that's what they're asking me to find. Subtract 1 from both sides gives me 9. Subtract the dz dx. And here is my dy dx. Slightly more challenging example is to find dx dz. In this case, dz tells me z is the independent variable. So that means anything not z needs chain rule. So the derivative of x is 1, but that's not a z, so I need dx dz. Plus derivative of y is 1, but that's not a z, so I need dy dz. And derivative of z is 1. That is a z, so I don't need the chain rule. Equals derivative of 10x is 10, but x is not a z, so I need a dx dz. Then to isolate dx dz, I actually need to get them all on one side first. So I'm going to subtract the 1 dx dz from both sides. So I'm going to have dy dz plus 1 equals 9 dx dz. And then I can divide both sides by 9, and dy dz plus 1 all over 9 equals dx dz. And there we have that one. So I'm going to save some of the other examples for a different video so that you have a chance to see them and just take a little bit of a break between videos here.